Let's talk about linear approximation for a moment. It turns out this is a very, very important concept that is very useful for many actual physical examples. And it can be very useful in application. So let's talk, before we do any actual work or any examples, let's just talk about the general concept of linear approximation and linearizing a function. Okay? So let's start with the classic example of the square root function. Okay? So if I have this, my function f of x is the square root of x. Okay? I've drawn the square root function. It looks something like this. And what I'm going to do is I'm going to take a look at my x value 2 and some kind of interval nearby 2. So the idea is, if I take this 2, and this could work for any nonlinear function, but let's just talk about the square root function. This is clearly a nonlinear function, right? It's not a line at all. It curves. Okay? And if I take this small interval around 2 and I zoom in, okay, and I zoom way in, and I have this picture over here. I've stretched the interval and I've zoomed way into the function, okay? If I zoom into this function right at 2, actually it's going to be linear. It's really a line. You can kind of see that here. If I zoom far enough in, it's actually going to be a line. And in fact, this works for any nonlinear function, but in particular for my square root function, okay? So if I zoom in far enough, it's actually a line. And the idea is that as long as we are close by some particular value, some input, let's say 2, as long as we're within some kind of small interval around 2, the function behaves like a linear function. Okay? And this will work for any nonlinear function. Right? You take any function, and if you zoom in close enough, it looks like it's linear. And it's the same concept with, if you think of the Earth. Okay, the Earth is certainly a sphere, but if we zoom in to one point on the Earth and we live our lives, on one point on the Earth's surface, we think of it as flat. Okay, go to North Dakota, that's a flat area. Okay, but we know that if we zoom out, it's actually a sphere. Okay, and the same thing works in mathematics. If we zoom in close enough to any nonlinear function, okay, for close enough values around some particular value, in this case 2, if I zoom in close enough, then any function behaves like a linear function. Okay? And this is a way to approximate the behavior of a function in a linear way. And we like this because linear functions are very easy to deal with. They're very easy to model, and they behave very nicely. Okay, so this has a lot of very important applied applications that you may see later. Okay, but for now, let's just talk about what this means and how to solve problems with this idea. Okay, so this is linear approximation, and by zooming up close enough, I can what's called linearize any particular non-linear function. Okay, and what's nice about this, we could use the ideas of calculus to actually get an approximation for any nonlinear function nearby some particular point. So in particular, we can use the fact that we know that at one particular value, I know of one line that touches my function at that one point, in this case 2. And that line is by definition the tangent line, right? We know that a tangent line means that it touches the function at one point, at this 1.2. The one point that I'm talking about is the value 2, the x value 2, right? So if I zoom in close enough, that tangent line really looks just like the actual function, right? If I zoom in close enough, the actual function really can be approximated by this linear function. This linear function is in fact the equation of the tangent line. Okay? The equation of the tangent line at the value 2, okay, for this particular function. Now let's look at a more specific example of linear approximation, and we're not going to take just one value 2, but let's just kill all the birds with one stone, like we usually do, and write down a general formula for how this might work for every single nonlinear function that you could think of, okay, in one variable. And it'll work for every single function and every single point that you may have. Now, you may have to go very close to that point, but as long as you're close enough to that one point, any function, no matter what it is, can be approximated using this idea. Can be approximated by the equation of the tangent line. So we make it a linear function. Okay, we're linearizing the function. Okay, so let's look at a more specific example.